Okay, hello everybody. My name is Aditya Pande and I study in IIIT Sricity, currently pursuing computer science engineering. And in today's lecture, we are going to cover P block elements and particularly group 13, 14, and 15. In the next lecture, we'll cover group 16, 17, and 18. Okay. So before we start off, let's just list out some of the properties that we know about p block elements. So we know this, our whole periodic table, let us say it is something like this, right? So this part, you have your S block. Here you have your transition metals. And then in the ending of the periodic table comes your P block. Now, the general electronic configuration that you find for a P block element is Ns2, Np, and now P can hold 6 electrons because we are talking about P orbitals, and P orbitals looks like this, and they can store 6 electrons, right? Okay, with this much in mind, I would like to start the topic. This is the brief general overview on P block elements. Now, remember that we are doing inorganic chemistry over here. So you have to learn the NCERT. The NCERT is your best friend when it comes to inorganic chemistry. And whatever we have, I have put in the slides is kind of a summary and an overview on all the important things that we have to do, okay, that you need to do in the particular groups that we are going to discuss. It is still advised that once you see this lecture, please go read the NCERT so that you can get to know everything in a greater detail. Okay, so let us start with group 13. Now, group 13 is generally also known as the boron family. Okay. Now, their elements that are present in group 13 are boron, aluminium, gallium, indium, and thallium. Now, because this is the first group present in the p block elements, that's why you have only one electron in the p orbital. Hence, the general electronic configuration of the group 13 elements are actually Ns2, Np1. Okay. Now, a common oxidation state that this group generally shows is +3 or +1. Okay. +1 comes more towards these down elements, and up we see more of +3. We know aluminium is a very good example because aluminium is always seen as a +3 option, right? So aluminium always shows +3. Now, let us talk why we also see a +1. So we also see a +1 because of a thing called inert pair effect. Basically, what happens is, we have Ns2, Np1. So this is my s orbital, and let's say my p orbital comes over here, which currently has only one electron in it. Now, what happens when you come down in these heavier elements? This electron goes, but then this electron, because there is a mixture, okay, there is a mixture. What happens is you have a shielding effect mixture of the electrons, and you have the nucleus also pulling the electrons towards itself. Now, because of this, these electrons do not participate in reactions. That is why only one electron from the p block is participating, and that is why you see this +1 oxidation state. So if you want to know about the inert pair effect, here it is. Okay, this is the inert pair effect. So what is the definition? Refers to the reluctance of s electrons in the outermost electron shells to participate in chemical reactions, right? What is observed as we go down the group? That means, let me just clear everything over here. As you go from boron to thallium, as you go from boron to thallium, you will see that the elements tend to exhibit a tendency where s electrons are likely to be involved, right? Why? Because of the difference in the effective nuclear charge, right? As we go down, the number of inner electrons increase, and from the attractive force of the nuclear
Recording in progress. Recording in progress.
Then we will come back to this page particularly just to see the physical properties. Okay. So this is the table. Now we have boron, aluminium, gallium, indium, thallium, and yes, I have taken it directly from the NCERT because NCERT is the godfather of inorganic chemistry. You can say like that. Okay. Now the electronic configuration is also a thing. As we go down, we know the mass of our compounds increases. Similarly, as we go down, the ionic radius increases. Now, this is the ionic radius of the +3 oxidation state. This is the one of the +1 oxidation state. And as we go down, the ionization enthalpy decreases. But you can a little bit see that aluminium and gallium kind of don't follow the general trend. We can see that the ionization enthalpy of aluminium is actually numerically less than the ionization enthalpy of gallium. Now, why is it so? That is written here. Because of the poor shielding effect that takes place between gallium and aluminium. Because there is a very poor shielding effect in gallium, in aluminium compared to that in gallium. That is why you see that there is a difference in the electronegative ionization enthalpies. And similarly, as we go down, the ionization enthalpy is decreasing, but you see it has decreased to a good extent here, and then it's actually increasing. Okay, now this part is kind of explained because of the inert pair effect, and this part is explained because of the shielding caused for the aluminium. And density follows a normal trend of increasing down the group. And smelting point and boiling point, you can see gallium has a very less melting point. Okay, that can be a question that can actually be asked. Then that is like which of the following elements in the group 13 in group 13 has a less melting point and similarly boiling point. Then these things are not so important because generally the standard electrode potential is given to you in the questions, particularly in electrochemistry. So you actually don't need to remember this, and you don't need to remember anything as a value. Like you don't need to know the values in particular, but it is advised to actually write down what is the general trend that the atomic radius is actually for gallium is less than that of aluminium. And why is that? Because we talked about the shielding that is caused over here. Now you can write that down, you can note it, and particularly note about aluminium and gallium. This is a good approach to solve inorganic chemistry. That is writing down everything. So now what conclusion do we come here? There are some anomalies in the ionization energy. Electronegativity decreases down the group, but it decreases but increases in an order. Like we saw, right? It decreases for aluminium, but increases after that slowly and slightly. And obviously, they are higher density. They have a higher density compared to our group 2 elements, which were our S block elements, right? Group 1 and 2. And acid-base characteristic change, the metallic character increases as we go down. We all know this particular point always stands, right? So primarily what you have to remember here is mainly about aluminum and gallium, because this is where the whole thing gets tricky. And now let's talk about a bit of the reactivity. Now this is again overview, and again NCERT reading is advised. Basically, let's just overview, like talk about it. If we take a group 3 element, okay, group 13, sorry, if we take a group 13 element and react it with oxygen, we'll kind of get an oxide. That is common sense, right? But we know that starting we get the plus 3, and in the end we kind of get the plus 1 oxidation state. That is why you see that thallium, sorry, which is this, actually forms a different thing, right? Actually, it forms a different product. Comparatively, aluminium would have preferably formed Al2CO3, right? And that is basically what this is kind of telling you over here also. Okay, this is because why are we getting these two kinds of oxide? You can all blame it on inert pair effect. Similarly, as we move down the group, elements of group 13 start reacting more vigorously with oxygen. Boron in crystalline form does not react with oxygen. This is an important point. And fine split amorphous boron combines with oxygen to generate B2O3. This is an important compound of boron. Okay. And aluminium would react with air thermodynamically. See, thermodynamically speaking, aluminium should react with air, but it does not. And the question is why? Because Al2O3 that kind of like forms a protective layer over aluminium. So if this part is my aluminium, my Al2O3 kind of like forms like this. And then this makes a protective layer that is present on top of the metal. And that protective layer kind of doesn't let the metal get exposed. So the metal is chemically inert. Okay. Similarly, if we react it with acids and alkalis, now acid, particularly HNO3, it gives rise to H3BO3, which we call orthoboric acid, right? Or in general, a more general name, boric acid. Okay. So this is an important reaction. I mean, yeah. Boron does not react with alkali, NaOH and KOH up to this particular temperature. But if you cross this particular temperature point, then you'll actually get K3BO3. Now that K is because we are using KOH. If you would have used NaOH, you would have probably got Na3BO3. Same thing. Okay, K and Na can be like used interchangeably. Okay. Now the other elements of group 13 react with both the non-oxidizing and oxidizing acid to release hydrogen gas. Okay. Simple. Mainly we were just, this reaction is important because this is the preparation of orthoboric acid. Okay. And here this point, crystalline form of boron does not react with oxygen. Now, reactions with halides. Now, we know the halogens, right? The halogens are basically my fluorine, chlorine, bromine, iodine, which is basically in my 17th group, right? Now, Ti, okay, just remember Ti, okay? Ti is a very important compound because this man here, this personality shows us an inert pair effect. And inert pair effect basically causes a big chaos in the end because of a lot of things, right? Now, halogens generally form AlMx3. Now, if you're getting confused with M, you can always consider aluminium because now it will just become AlCl3, which is a familiar compound to you. So this is what generally it forms with all the compounds. Okay, with all the halogens, it forms trihalides. But titanium dude, this dude, Ti dude, he only produces TiF3 and TiCl3. Other than that, he doesn't produce anything. Okay, my friends. Now let's talk about reactivity with water. So we saw B2O3 here up in the previous slides, right? Here, boron combines with oxygen to produce B2O3, and that's particularly the fine split amorphous boron. Now, this is another way to create boron, B2O3. and that is just hydrolyzing boron. Okay. And aluminium decomposes cold water to produce hydrogen gas in the absence of the oxide layer. Gallium and indium will only react with water in the presence of oxygen gas. In moist, thallium forms TiOH. Okay, so TiOH is formed when there is moist air, and gallium indium only react with water when oxygen is present. Basically, everyone kind of reacts with water, but they have their few here and there limitations. Okay. Similarly, reactivity towards metals. So when boron reacts with a metal, it forms borides, right? Group 13 remaining elements basically are apprehensive of mixing with metals. Basically, you take a metal, you react it with this, so they'll mix. Kind of like because they are also a bit metallic in nature, kind, right? You know, aluminium. Aluminium is like the go-to thing if you want to understand anything about group 13. And Mg is basically this particular reaction kind of shows the, here it's written, non-metallic character of boron. Okay, boron forms borides. These are called borides. So you can keep it in mind, right? The main thing that you need to keep is B2O3 because this is the preparations of B2O3 and an exception of Ti because it only produces it in moist air. Now, boron. Let's talk a bit about boron, okay? So now we saw boron can be prepared from a lot of things, okay? And boron is one of the elements that shows a non-metallic character that is in group 13. And primarily it is the first compound over there. Okay. Now there is another thing I wanted to tell you is why is boron exhibiting an anomalous behavior? If you observe that boron will actually show a very weird behavior compared to the whole other group. Okay. The remaining elements of the group kind of like are still compared to the remaining elements of the group, boron shows very weird and anomalous properties. And the reason is written in the first slide. It's basically boron exhibits anomalous behavior because of its small size, its high ionization enthalpy, its high electronegativity, and the most important, the absence of d orbital in its valence shell. So why does it do it? Particularly because of its small size. Because it has a small size, it has a high ionization enthalpy and a high electronegativity, and there is no d orbitals. Okay. Now let's talk about boron's preparations. So we just saw that because B2O3, you can use B2O3, put some metal around it, particularly like you could even use Mg. Mg has been used, you could use any other metal, and that will give you boron, right? Similarly, you could use boron trichloride because we saw that they form what? MX3 kind of halides, right? And then you can electrolysis of a fused mixture of boric anhydride. So B2O3 is kind of called a boric anhydride. And when you electrolyze this buddy over here and with a lot of different things like magnesium oxide, magnesium fluoride, maintaining a constant temperature of 1100, you can actually form boron. And obviously by the thermal decomposition of boron hydrides and halides. Okay, like here you see this is also example of thermal decomposition because you're using a high temperature over here. And same thing goes on with B2H6. So this is a hydride and this is an halide and this is kind of like just, in thermal decomposition is taking place. Now we come to a bit more important topic, I would say, and that in particular, my friends, is compounds of boron. Okay, and the first compound we'll talk about is orthoboric acid, right, which we saw over here, orthoboric acid, basically boron's reaction with concentrated HNO3. And orthoboric acid is called H3BO3. Okay. Now, I have not put the structure of orthoboric acid on the slides, but please look at the structure. Okay. This is one homework I'm giving you. Please look at the structure from NCERT. You will notice that it is actually a very cool kind of a structure, okay? Big structure. Okay. Anyways, let's talk about the preparations of orthoboric acid. So, orthoboric acid are prepared firstly from borax. This is a very common reaction and a pretty, well-known one also. What happens is you take borax, which is this, and you add sulfuric acid and water. So you get orthoboric acid and along with that Na2SO4. A less common reaction, this one was actually given in my reference book also when I had done that, is one using coalmanite. So this is coalmanite, this buddy over here. And this dude reacts with sulfur dioxide and water to give you calcium hydrogen sulfite, and boric acid or orthoboric acid. But the important thing about boric acid is basically not its preparation, but its properties. Because boric acid, gives us boron trioxide, which is B2O3 again, right? So what happens is you use boric acid and you kind of heat it. So when you heat anything, what happens is dehydration takes place. Now dehydration means an H2O goes. So this becomes HbO2, which you can see on the slides over here. I'll clear it. HbO2 over here. Now what happens? You again heat it and again water will go. But what will happen this time is two of these things will come together. Two of these dudes will come together and kind of like form a tetraboric acid. A lot of these dudes will come together, basically. Okay? Because you want H2O to go, so you need H2O, right? You don't have 2H over here. So, yeah, you need more of those metaboric acids, and that will again cause dehydration. And again, you will, keep heating it, and you'll get boron trioxide. So, from the process of H3BO3 to becoming B2O3, all you're doing is heating it the whole time. But in the middle, there is a metaboric acid form, there is a tetraboric acid form too. Okay. And also an important thing is that boric acid is a very weak monobasic acid. And because it is a weak monobasic acid, on titration with NaOH, it gives sodium metaborate, which is this. Okay. And other than that, here are a few other reactions like reaction with metal oxides, basically like MO, or probably you can just say Al2O3 kinds, right? So what happens is boric acid. Oh yeah, remember that this is also another version of writing boric acid. Okay. So generally, if you just see this somewhere, don't get intimidated by it and kind of just, it forms M borates and M is a bivalent metal. Okay, so not a trivalent. This is a trivalent. Maybe calcium oxide would be a cool example for this. Okay. And similarly, aluminium borofluoride, which is BF3. Basically, in the end, that kind of forms. Aluminium borofluoride is this dude. Sorry, ammonium borofluoride is this dude over here. NH4HF2. And then that kind of forms BF3 in the end. So this is a preparation of BF3. Okay. Another one we talked about borax. So we kind of like saw borax over here, but this is dehydrated borax. Borax is generally in this form. Okay. And we just saw like, see, you can use HbO3, which is HbO3, I'm telling, sorry, H3BO3, and you can react it with Na2CO3 to give Na2B4O7, which is your borax. And basically, there are a few important properties of borax. Firstly, let's just talk about the easier one, the heating one. You heat it, the water goes, and again you heat it and it breaks down and gives you B2O3. So there are two methods of becoming B2, getting B2O3, which we already found. One using H3BO3 and one using this particular method. Also, aqueous solution of borax is alkaline in nature. Okay. And why is it alkaline in nature? Because of the hydrolysis that is taking place. Okay. Now let's talk about B2H6. B2H6 is basically BH3. Okay, BH3 is a hydride of boron, and you get two such hydrides, and that kind of forms a bond between them. So you have BHHH, H, B, H, H. It kind of like two BH3 things come together, and then that forms a bond like this. It forms a very close kind of a diamond type thing, which you would say if you see it from a top perspective. And like not diamond, rhombical. But yeah, this is kind of a chain. Again, NCERT for the structure, but overall it is something like this. And also diborane, it's not borate, it's borane. How can you prepare it? You can just, take BF3, react it with LiAlH4, and what happens is you get B2H6K2 molecules. Same thing, you can use NaBH4 along with, sulfuric acid or phosphoric acid, and you will get diborane. And diborane with water gives basically, orthoboric acid. Kind of like when you're hydrolyzing a hydride, you get a acid. That is simply the same thing. Similarly, we have aluminium, and aluminium is like, generally the common properties is that it executes a plus three structure, and that is the most important thing. And also here, first we'll talk about AlCl3. So this is the structure of AlCl3. Now we have seen when we learned organic that AlCl3 is kind of electrophilic. That means it has a shortage of electrons, right? Now that is because of the empty orbitals that is present of this brother over here. Okay. So what happens is it chlorine kind of becomes a good guy and donates his bond, and this kind of makes this type of a structure. Now you replace this with whatever other groups you want, CH3 or anything. That's pretty cool, right? Hydrolysis of this gives AlOH3, and heating of AlCl3 kind of again gives AlOH3 and AlO2O3, right? Talking about Al2O3, this is Al2O3. Okay, Al2O3 is aluminum oxide or alumina, and kind of like we have seen this in a lot of very other chap. We have seen it in a lot of other chapters, right? So how do you prepare it? You just heat AlOH3. You'll get Al2O3, AlSO4 thrice, meaning aluminium sulfate. You'll get this, and this big compound. I think this is more salt. Okay. This big compound you use, you will basically get a big set of compounds in which one of the compounds that you get is Al2O3. Okay. So I hope it's clear. Next we have group 14, but before that, I'll just like to tell what are the important things you want to know here. You want to know the structures of H3BO3, structure of AlCl3. Generally, AlCH3 thrice is also asked sometimes. And you want to know the structure of B2H6. Most of it is given in your NCERT. I'm not sure about this one, AlCH3 thrice. But yeah, other than this, the more important ones, these three are definitely given in the NCERT. So kindly look for it, okay? Now, because kind of like the rules and regulations of how it goes about in group 13, group 14 can actually be completed a bit more quicker. Basically, you have carbon, silicon, germanium, titanium, I'm telling, tin and lead. And the general electronic configuration, because group 13 had one electron in its p orbital, group 14 has two. Okay. And the general oxidation states are +4 and +2. And +4, +2 again comes down to inert pair effect, +2 from +4. And again, as we saw in boron, because of the same reasons, even carbon has an anomalous behavior compared to its other companions in this group. And chemical properties, you can just see it from the table, the physical properties, right? So there is not much of an electronegativity difference between silicon, germanium, tin. There is quite a difference between the densities as we go down, but just see carbon is a bit more dense, okay? Carbon is a bit more dense than silicon. Other than that, it increases as we go down the group. Again, ionization enthalpy decreases as we go down the group. Same with the radius. You can see the radius is kind of increasing as we are going along down the group, right? And there is no anomalous behavior over here. Everything is going down in a general fashion. So that is like a very, straightforward thing. Okay. There are not much of an anomaly kind of a thing, right? Again, it forms hydrides, oxides, and halides, kind of like how we saw it over here in this case. So the reaction, I'll not be covering it because it's kind of the same logic that we saw in group 13. What I will definitely be covering is some important compounds of carbon and silicon. So basically, let's talk about carbon monoxide. So carbon monoxide is a very harmful gas, right? It can cause a lot of damage. We all know that is the general thing. But how is this dude kind of prepared? So one way of preparing this dude is just limited supply combustion of carbon, and then you can heat a certain oxides and you'll get heat certain oxides and you'll get, and you can pass steam over hot coke, and this is called, this combination of CO and H2 that you get is called water gas, right? This is an important reaction. And similarly, passing air over hot coke, that is basically this reaction, the producer gas that is formed, CO plus N2 is the producer gas, CO plus H2 is the water gas. These two reactions are important, okay? Because there are many questions where they directly use the term water gas and producer gas and not this. Okay, so that is something you need to keep in mind from your point of view, that we have water gas and we have producer gas that is going on over here. And properties of carbon monoxide kind of like, see, firstly, it is a very good reducing agent. Okay. So most of your oxides are generally reduced to metals when you use um, carbon monoxide, and it burns in air completely to give CO2. Basically, what happens is CO2 plus O2 should have given you CO2 if it would have completely combustion. But because you're limiting this man's supply over here, it becomes CO. Right? Now you continue the combustion, it will become CO2, right? Because in eventually it had to be that only. Right? Now, like they don't ask this much, but just for, just for the situation, if it ever comes up, test for carbon monoxide. It burns with a blue flame and it turns filter paper soaked in platinum in pink, or if it is palladium, it becomes green. Okay, so platinum becomes pink, palladium becomes green. Just keep that in mind. And we'll even talk about carbon dioxide over here. So carbon dioxide, we all know this compound pretty well. It is CO2. It is slightly acidic in nature. It is a product that we give out after respiration, right? And kind of like the preparations are also pretty well known to us. Basically, you take any carbonate, right? Any form of carbonate, be it Na2CO3 or NaHCO3, that is your bicarbonates. This carbonates and bicarbonates always give carbon dioxide out. Similar is the combustion. We just talked about this reaction in the previous slide. And what are some important properties? The most famous one is lime water turning milky, right? So lime water turns milky when you pass carbon dioxide through it, because it kind of like forms a CaCO3 compound, okay? When when you add like excess CO2, you add more and more CO2, what happens is the CaCO3 that is formed kind of turns into CaHCO3. Now the CaHCO3 does not have that milkiness kind of a thing that CaCO3 has. So CaHCO3, when it's formed, the milkiness disappears, okay? And dry ice, which you also see which is basically solid carbon dioxide or dry ice, which we see in our fire extinguisher. So if you people have seen fire extinguisher, right, it is kind of a thing that has here, and it's some white color thing like comes out, and wherever there's fire, it puts a stop to that fire. So what that white color powder that is basically coming out, that is dry ice, and it is called dry ice because when it comes out, it comes from a solid state and it directly becomes a gaseous into its gaseous states without liquefying. So it's kind of that's why it's called dry ice. And what happens? How do you prepare dry ice? You basically cool CO2 under pressure. So you put a great amount of pressure and you cool CO2 down, and that becomes dry ice. Okay, carbides are also a pretty important structure when it comes to talking about the compounds of carbon, primarily because of AlCsC2, Al4C3, and Be2C2. Sorry, Be2C. Right now, salt, these are carbide salts. Sometimes you have covalent carbides also, like SiC. That is basically called a carborundum. Carborundum. Okay. Now, basically, what happens? These here, silicon and carbon are joined together because of a covalent bond. Okay, this gets me to another property that I just got in my head and I have not written it in the slides, is the tendency of group 14 to show long chain formation. Okay, the chain formations that we see, okay, the chain formations that we see in our organic compounds, the big chain formations, that is a property that kind of like starts from group 14, which is kind of obvious, but yeah. Similarly, we have interstitial carbides that is basically formed when a transition metal and carbide ion, that is your acetylide ion, comes off together. That kind of forms an interstitial carbide. Now let's talk about compounds of silicon. Now silicon has primarily two important compounds. Silicon, man, mainly and two different forms you find oxides of silicons. Okay, main is silicates and silicones. So silicate kind of like shows this 3D structure, and silicon is kind of in this structure, the big chain kind of a structure. Now, just see silicon polymers contain SOSI linkage. So we can see this is an SOSI linkage over here that is formed by the hydrolysis of alkyl or aryl substituted chlorosilanes. Okay. And silicates are basically salts of silicic acid. That is this dude over here. So it has SiO4 tetrahedral structure रहता है, and that is why because it is tetrahedral you see this kind of being like that. Okay. And another important compound would be Na2SiO3, right, which we call sodium silicate. And that is simply prepared by passing SiO3, that is another oxide of silicon, to Na2CO3. Okay. So that kind of like completes group 14 also. Particularly, you have to just know silicones, silicates, and compounds of carbon over here. And again, I would just say, please go through the NCERT ones. Okay. And now let's go on to group 15. That is basically the nitrogen family over here. And there's a lot of things written in this page. So let's just see. Firstly, the elements present in group 15: nitrogen, phosphorus, arsenic, antimony, and bismuth. And very similar to, the group 13 and 14 that we have studied. We are kind of, it's the almost the same properties over here. And basically, you kind of like see a bit of a transition also over here, right? So what happens is nitrogen and phosphorus, they are completely non-metallic. Arsenic and antimony are metalloids. Now, what are metalloids? They, at some instances, they show metallic characteristics, and at some instances, they show non-metallic characteristics. Basically, such compounds are called as metalloids. Okay. And finally, we have bismuth, the final guy in the whole group. And that dude is completely metallic in nature, right? And obviously, because it is the third element present in our P block, we have NP3. Now look at this structure, my friends. Just look at this, okay? You have NS2, you have firstly NS2. So that is a completely filled. And if you see this, this is your s orbital, this is your p orbital. S orbital is completely filled. And if you see p orbitals quite, properly, you will notice that p orbitals are half filled. So this kind of like makes group 15 stabler compared to group 14 and group 13. And similarly, group 16 and 17, because it is more stable compared to them. If we see their, properties will actually have numerically greater values than that of the other ones. Now, as we go from left to right, we know these properties increases. But let's say just group 15 and 16 are there. So 16 has numerically less property compared to 15, because 15 is stabilized because of the half and the full orbitals. Okay. So that is a thing to keep in mind. And the other things are, there are common oxidation state like -3, +3, +5 are very, very common oxidation states. And we'll talk about nitrogen and phosphorus in a greater detail, because these are like one of the two most important compounds of group 15. And obviously, we are talking about hydrides over here because these are important hydrides, particularly ammonia and phosphine, which is pH 3. Phosphine is pH 3 and ammonia obviously NH3, right? So now what happens is, as you know, you go from nitrogen, oh, it's right there, nitrogen to phosphorus to arsenic to antimony to bismuth. Firstly, bismuth does not form hydride, so we'll just cut out bismuth right now. Now, as we go down, the melting point increases. Now, why is the boiling point of nitrogen so high compared to this and this? Right? As we go down, the boiling point should increase because the mass increases. But when it comes to nitrogen, this man shows a thing called hydrogen bonding. Because of hydrogen bonding present in ammonia, the boiling point actually is very, very high compared to the other elements that are present over there in that compound. Right? It still could not beat antimony in the mass combat, but it could beat phosphorus and arsenic hydrides, but just because it had hydrogen bonding. Okay, so just keep that in mind, right? Other than that, the bond length, the bond energy, and the bond angles are quite like the obvious thing over here. Right? The most important thing here was just the boiling point, because this dude over here, NH3 man, shows hydrogen bonding. Let's talk about nitrogen a bit, and particularly I want you to focus on this table the most, okay, when we come to it. Now, preparations of nitrogen, very straightforward reactions. You take CO, ammonia, heat it, it gives you N2Cu. You take COCl2, ammonia, and that gives you CaCl2. And you can basically take ammonium nitrate, heat it, and you will get N2, dinitrogen. Okay. Then basic the properties of dinitrogen, basically on oxidation, it gives NO, right? It forms nitride with lithium, magnesium, calcium, and aluminium, and it reacts with carbide to form calcium cyanide. Okay. Now in NCERT, they have given you a reason of N triple bond N being a good decision of nitrogen, kind of like why it has that and why it is, it has a high ionization enthalpy and everything, and why it forms a triple bond. So just see, it is like two lines of NCERT are given at the start of dinitrogen. Now let's come on oxides. Now here are the important things, okay? These oxides in nitrogen exhibit different properties, and like there are a lot of things that could just, be a dimer of one. Like if you see, you know N2, NO2, you can write N2O4, okay? Now, each of these oxides, they have a respective color of themselves. They have a respective preparation reaction for themselves, and they have a respective structure, which you should know very well, because that is generally asked in resonance questions, because resonance is kind of like very possible over here because of the minus charge over here and the double bonds that are generally formed. And that is why you should evidently know a lot about nitrogen oxides in particular, right? And one, so a few things that you'll have to see from the next table in NCERT, and this is just to make a practice for you to read NCERT, that I want you to read, and particularly about which is acidic and which is not, what is the color, and what is the particular method of preparations. Right, so this table is present in the NCERTs, and for your practice, kindly go through that table. And obviously, we have oxy acids, basically the acids of HNO3. And again, quite straightforward, hyponitrous, hydronitrous, nitrous, nitric, and trinitric, out of which nitrous and nitric are the most important oxyacids of nitrogen that are present. Another important compound of nitrogen, other than these oxides and these acids, was ammonia. It's hydride, right? And this is kind of the Lewis structure of ammonia. And ammonia is a very important compound because we use ammonia for a lot of things. And that is why you see we have a lot of detail about ammonia. And next page, if you see phosphorus in particular, right? So ammonia, basically the preparations is just ammonium chloride, NaOH makes ammonia. Similarly, magnesium nitride, when you hydrolyze it, it gives ammonia. And Haber's process, right? Haber's process is kind of very important because it is a very frequently asked process. And if we talk about properties of ammonia, ammonia is basic in nature. We all know that. And to prove it, we kind of just hydrolyze it, and that gives ammonium and a hydroxyl ion. And because it gives an hydroxyl ion, it is basic in nature. That is kind of a proof. Now, ammonia reacts with halogens, kind of like all of them. And what happens is there are two possibilities, right? Either the halogen is in excess, or either ammonia is in excess. Any one of it will be at excess in one time, right? Now, if your halogen is in excess, then it forms basically NX3 types. If not, it will just, if our no, ammonia is in excess, it just kind of like forms NH4X. Okay. And that is an evident example with chlorine. Similarly with bromine. And when it comes to iodine, it forms NH3Ni3 and Hi. And when you again, you take 8 molecules of NH3Ni and that forms NH4, ammonium iodide. Okay. It forms a lot of important complexes that we have seen in coordination compounds. And basically, it helps in the precipitation of heavy metal ions. Okay, so when you take ammonium hydroxide, which is another compound that can be formed using ammonia, right? So ammonium hydroxide we know is used in the tests, right? We use sodium hydroxide and ammonium hydroxide for our analytical tests of salts. And at that time, you have to remember brown, white, green color PPT of whatnot. So ammonium hydroxide that you use for those tests also kind of comes from here. Now let's talk about phosphorus quickly. And phosphorus, there are three kinds: white, red, and black phosphorus. And it kind of does the heating. Like, each of them are allotropes of each other. And white phosphorus, red phosphorus, and black, it's like white becomes black and sorry, red, and then red becomes black, right? And kind of like white has a structure like this, black has a structure like this. Okay. And again, you can refer to the NCRT. This is just an overall thing. Similarly, we have phosphine, which is the ammonium equivalent for phosphorus. And you have different methods of preparing phosphine like this. This method, the first one using Ca3P2, this has a name. Kindly find the name out in NCERT. And other than that, common methods using phosphoric acid, P4 and PH4I. This is also an important method. And phosphorus has some property like forming phosphorus iodides, PH4I, this dude, and basically combustion of it, which gives me H3PO4. Okay. Now talking about oxides of phosphorus, we have P4O10, and P4O10 has a structure like this. I have personally, put this structure over here because it is a very important structure. We talk about bridge oxygen atoms over here. We'll see a question on that. And other than that, we again have its reaction. It will form PCl3, PCl5 with chlorine and even SOCl2. So you can use SOCl2 to form PCl3 and PCl5 also. All right. And again, a few more reactions. And basically what happens is when we come to phosphorus, nitrogen, oxygen, the number of reactions about its application, like you see here, we are using PCl3, PCl5, kind of like increases. However, they don't ask much of this thing. JEE goes comparatively simpler, but then it is listed here because it is listed in some or the other book regarding this topic. Okay. And you can see various forms of like, you take the oxide, react it with HNO3, you get N2O5, or you take the oxide, react it with H2SO4, you get SO3. So this is a very, complete to the box diagram. Again, they don't ask this, but they definitely ask like what is white, red, and black, and the structure differences between them. And again, the acids, phosphorus acid, hypophosphoric acid, phosphoric acid, pyrophosphoric acid, and metaphosphoric acid. Okay, we have basically, just an summary kind of thing about the three groups over here. And reactions are definitely done, which are very common and which are frequently kind of asked reactions. And it would definitely be advised that you see the NCERT first for these particular chapters. Coming, let's do this question. The total number of compounds having at least one bridging oxo group among the molecule. Now, what is a bridging oxo group? Okay. So you see this compound, okay? P4O10, the structure. So you have POP, right? So POP, this is the kind of a thing. The oxygen forms a bridge between that. So all you kind of have to do is make the Lewis structure of how many are these? 1, 2, 3, 4, 5, 6, 7, 8. 8 of them, and then you have to see how many have it. Okay. Later, when the slides will be shared with you, actually, I have already made this, like taken the structures over here. So N2O3 kind of like forms a structure with a little bit of ketoenol tautomerism here. So you can see N2O3 has and bridging oxygen bond right here. N2O5 has. I just showed it to you in P4O6 and P4O7. We saw it in P4O10, but it's kind of the same. And H2P2O5, and we saw it in H5P3O10. Right? All of them are like, if you know how to draw orthophosphoric acid, you can kind of like draw it over there. But basically what happens is you have to remember the structures. Now, main structures that you need to remember are discussed in the previous slide over here, and that is P4O6 and P4O10. Okay, that is always like the standard go-to question for any JEE question. And similarly, this is the case over here, right? So these structures were discussed in your nitrogen right here. So you can see this is a past year JEE questions. Okay, this is a JEE advanced question if I have to be honest. But yeah, so you don't even actually need to know the structures. If you have a good holdover drawing Louis structures, you can pretty much finish this question pretty easily. But then, yeah, because these structures were discussed in the most of the structures were discussed how to draw. in this topic, and that their structures are also given in your NCERT and other reference books as such. We have simply included it over here. Okay. So answer here is 6. Next, among the following, which of the following is a correct statement? The Lewis acid AlCH3 is a 3-center 2-electron bonds. It is dimeric in structure. Acidity of BlCl3 is greater than that of AlCl3. Yes, we have seen this because my friend's boron kind of like behaves in a very anomalous way. So this is kind of an obvious thing. Not this. AlCl3 has a 3-center 2-electron bond. It is dimeric structure, and BH3 has a 3-center 2-electron bonds. So now you know what is the structure of these. So this is the structure of AlCH3, right? So you can see what happens is you have 3 centers over here: aluminium, carbon, and this aluminium. This kind of like comes together, and there are 2 electron bonds, this one bond and this one bond. This is called a 3-center 2-electron bonds, and kind of like we also call this a banana bond. Okay, this is also known as a banana bond, but the most important one is the 3-center 2-electron bonds. Now, if you see AlCl3, it does not have a 3-center 2-electron bonds, right? Sorry, it has a 3-center 2-electron bonds here. But if we see in BH3, that is kind of not the case, okay? Because this is where the sharing is happening. It's not like this. So this is 2 separate bond sharing that is happening. Whereas what happens is here, it's kind of here. Okay. So the answer is what? A, B, and D. Okay, 3-center 2-electron bonds is not present over here, and 3-center 2-electron bonds is present over here. Okay, so this is a banana. This is called the banana bond. Please keep in mind, and then this is the thing. Next question: increasing order of atomic radii. We saw that obviously, because it's not considering boron. Then we come here. Then we know it's gallium. Then aluminium. You can clearly tell because gallium has to be less than aluminium, which is only in this particular option. So option B is the correct answer. And the final question: the stability of hydrides. Now, here's the thing, okay? The hydrides are extremely stable, and nitrogen is additionally extremely stable thanks to its hydrogen bonding property. The hydrogen bonding actually enables us to, have a lot of stability, hence increasing its boiling point also. So nitrogen kind of like, has to be on the top. Then as we go down, okay, we see that the central metal atom actually become big. The bigger the atom gets, smaller the hydrogen gets, right? So this polarization kind of like takes place, and which you have probably done in your S blocks. So polarization takes place, and what happens is that you will start seeing instability, right? Within the hydrides, you'll see instability as we go down. Hence, for this one, your answer is A. Okay. Basically, nitrogen has to be on the top thanks to its hydrogen bonding properties. And as we go down, the size of our central atom increases, which in turn, compared to the small hydrogen atoms, causes polarization, and that is basically why it becomes unstable. Final question. Number of pi bonds in P4O10. So P4O10 structure is changed with you. Now you just need to calculate the pi bonds over here. Okay, that's pretty far. Okay, so just calculate the pi bonds. I know that you people know how to calculate the pi bonds, so I won't be teaching it to you over here, but it is actually a very simple thing. And your answer is 16. Okay, I think this should be sigma bonds then if it's 16. Okay, so just look for it, and then that is it for this particular lecture. I hope we could give you a basic idea of what are the important things and what aren't. And again, once I would advise you kindly read the NCERT for this particular topics, particularly inorganic chemistry. And till then, guys, take care and I'll see you in the next one. Thank you.